Hey everybody, it's Mr. Slomka. I got another lesson for you. It's 12-2, Techniques for Evaluating Limits. We started 12-2 on Friday, but we're picking it up again. We're doing a video lesson because we got some kids who are taking AP tests and they might need to catch up. So 12-2, there's no vocab or anything. We're just going to learn about some more techniques. So we have tables and we've got factoring, but what about some other things? So here's our first problem right here. It is the limit as x approaches 4 of x minus the square root of 3x plus 4 over x minus 4. Now you might say, well, my favorite technique is direct substitution. Can I use direct substitution? That's what I would try first. You can't. It doesn't work. The reason why it doesn't work is because if you try to take this 4 right here and you try to type it into the denominator, 4 minus 4 is 0, and you have an error message in your calculator, undefined. So that's not going to work. So then the other method that we learned about on Friday was the factoring method right here. So what happens if I try to factor it? Ooh, well, you can't. There is really nothing to factor, definitely not in the numerator or in the denominator. So that means that one's out of the question at this moment as well, too. So what's our new idea? Our new idea is to rationalize. You've got a square root right here, so it would make sense to rationalize. But the weird thing is to rationalize means to take a square root out of the denominator and put it in the numerator. That's already happening here. So what we're actually going to do is we are going to unrationalize. We're going to take the square root and move it down to the denominator, which is a little different. But we're going to do it in the same kind of way. So here's our square root right here. It's got an x with it as well. We need to multiply by a special case of 1 that uses that information. But it's going to use the conjugate, aka the opposite version. So it's going to be x plus the square root and x plus the square root on top and on bottom. Now that sign right there changed to a plus sign, but the stuff underneath the square root stays the exact same. So it's still going to be 3x plus 4. Cool. All right, now we're going to use some foiling. So when we're foiling this, there's lots of great stuff that happens in the numerator. It doesn't look like it would be that great, but it works out pretty nice. X times x is going to be x squared. Here's the really good part. X times this positive square root and x times this negative square root are going to cancel each other out, so you don't have to deal with it. Then the square root times the square root. It's still going to be negative because of that guy right there, but we're going to lose all of our square roots and it's just going to be 3x plus 4. If you take a look, I'm writing in parentheses. That's kind of important. Now in the denominator, if you're like, okay, well that one's going to be ugly, you're right. It is going to be ugly. It's so ugly that I really don't want to deal with it, so I'm not going to. I'm going to leave it exactly the way that it looks. I can always go back and FOIL it out later if I want to, but maybe I won't have to. Hint, hint, wink, wink. All right, let's do some more simplifying. So now I'm going to take this negative sign right here. Popular thing that happens is if you don't put the parentheses, only the 3 becomes negative. And that's true, it should be negative, but also the 4 needs to become negative as well. So both of those things are going to now change signs because of that negative sign right there. So it's now going to be negative 3x and minus 4 in your numerator. The denominator, I am still going to be lazy about, and I'm not going to change it at all. So it's going to be x minus 4, and it'll be x plus the square root of 3x plus 4. None changed. Cool. Now what we could do? Well, here's a funny thing. Remember earlier when we said that we could not factor? All of a sudden, now we can. We've got an x squared term, an x term, and a constant term. So now we're going to factor it. So now this becomes a no. Now it's going to become a yes. So two numbers that have a product of negative 4 and a sum of negative 3 are negative 4 and positive 1. So let's bring our work back up over here. Limit as x approaches 4, and we're going to factor that, which is going to be x minus 4 and x plus 1. There you go. Denominator, once again, still being lazy. And if you take a close look at what I'm writing down, you'll notice that my laziness is actually going to pay off right here, which is, for some people, a little bit of a surprise. Right here, we just created an x minus 4, and we've had an x minus 4 in the denominator for a while. So those two things are going to cancel out, and you no longer have to worry about them, which is awesome. Now my numerator is much smaller, just x plus 1, and my denominator is just x plus the square root, 3x plus 4. Cool. Okay, so now we have successfully unrationalized this problem. The square root is now back in the denominator. And it also means that we can now direct substitute. A while ago I said that no, I could not direct substitute, but now I can. So what's going to happen here is I'm going to take my 4 right here, and I'm going to plug it into the numerator, and I'm going to plug it into the denominator a couple of times, and we'll see what happens. So, up until this point, when I've done all my work, I've written limit as x approaches 4 every single time. And you must do that as well until this last step. When you use the direct substitution, you are essentially taking the limit, which means you do not need to write limit anymore. You are going to do it right now, so the action has taken place. You don't need to have this reminder that I'm going to do that in a little bit, but I haven't done it yet. So we are going to actually be taking the limit, and we don't need to write it. But you do need to write it for every step up until this point. So until you direct substitute, just keep on writing limit. So this numerator is going to simplify down. 4 plus 1 is just going to be 5. Down here in the denominator, 3 times 4 is 12, plus 4 more is 16. Square root of 16 is 4. 4 plus 4 is going to be 8. There is your nice fraction right there. It cannot be simplified, so that's it. There's your final answer right there, 5/8. So another important thing that I wanted to walk you through with this problem is just the thought process. So I like direct substitution. It's fast, so we tried that. I like factoring, so I would have tried that. And then I had to unrationalize because that was my next option. Let's do another problem similar to that. So here's another one right there. Same kind of thing. Let's go through the thought process. Direct substitution is my favorite way, but if I direct substitute here, it will not work because of the denominator. So that means it's out. Simplifying by factoring. Well, I don't have anything to factor here. There's no powers of 2 or anything, so that one's out as well. Darn, those are my favorite two techniques. Rationalizing, that's my new one, but that's only for square roots, and I don't have one of those, so that one's out as well. What's left? Well, the only thing you have really left in your arsenal right now is a table, and a table would be great, and I highly encourage you to use tables whenever you feel any kind of stress or unsureness, so use that table. But also, something you can do is you can use your calculator. So what I'm going to do is I'm going to use my calculator, and I'm going to use my calculator in radian mode because it's a sine cosine kind of thing, so you might want to check what mode it is. And then I'm going to type in the equation of my my limit right here. Then I'm going to use the zoom, and I'm going to choose a zoom option of 7 right there, option 7, and it's going to graph out my sine and my cosine wave right there. Now, we've had problems with the sines and cosine waves in the past. They oscillated violently, and that meant that the limit did not exist. But this is a nice oscillation right there. Very lazy, very predictable. You can see what's happening. It is easy to see what's going on. You can even sketch it, and you do a pretty nice job with your sketch. My sketch isn't great, but hopefully yours is better. Because of the niceness, I can tell that my graph is swooping up as I approach 0, and it's swooping down as I approach 0, and that means that I'm pretty sure that the y value right here, although it might not be, it sure looks like it's approaching, and that value ought to be 0. So the limit is going to be 0. So there you go. That one's a nice one. Use that graph right there, and you can see it. Here's another one. This last one down here at the bottom of the first page is the biggest one. This is an important one. This is a very, 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 very exciting example. This guy right here has got a lot going on. So let's break it down a little bit. This part right here in the middle with the f of 2 plus h minus the f of 2 over h, that's actually something that we did back in September. It's called function notation, and we simplified. And it was really good. You guys did a good job on it. And so it's back again. Now, the only new thing we're going to put on it is that it's now a limit, and when you take the limit of something like this, what you're actually doing is you're going to be calculating some of your very first derivatives, which is exciting because that's what the very beginning of calculus is all about. It's all about derivatives. So this is a weird-looking thing. I'll break it down for you. So right over here, the first thing I want to look at is actually over here. This is our rule. It says f of x is equal to 2x squared plus 1. And so what's going to happen here is that basically whatever goes into the parentheses here is what's going to go behind the 2 and in front of the power of 2. So it sits right there. Now over here, if you take a look, I picked some different things. So over here it says x, but I don't pick x anymore. What I'm going to do right here is I just have f of 2, so that means I'm going to be plugging a 2 in. And over here I'm going to pick something even stranger. I'm not just going to pick a letter, and I'm not just going to pick a number. I'm going to pick 2 plus h. And so what's going to happen is that we're going to kick that x out right there, and we're going to replace it with this whole chunk, 2 plus h. Let me show you. So I've basically got the limit exactly how it was before, but instead of using the f of and the f of here, I've actually used the pattern 2x squared plus 1, except I've got blanks here, 2 blank squared plus 1, and another 2 blank squared plus 1. What I'm going to do is I'm now going to take these two pieces, I'm going to plug them in. So the first one is going to be this guy right here. He's going to get dropped down, and it's going to be 2 times 2 plus h squared plus 1. And the other one is going to be this dude right here, and he's going to get dropped down, and it's going to be 2 times 2 squared plus 1. All right, now let's see if we can do a little algebra. So I'm going to hold off on the limit for right now. I'm just going to write it down. And I'm just going to try and simplify as much as I can. So right here, this is one of the first places I want to start. It's got a power of 2, so you should FOIL it. So that means it's going to start off with like 2 times 2, which is going to be 4. And then you'll have 2h, you'll have another 2h, which is going to be a 4h. And then you'll have h squared for your last term. You still have your plus 1 right there, so we'll hold on to that. And we'll still have our minus sign, so we'll hold on to that. Now inside the parentheses right here, if you're following the order of operations, 2 squared is 4. 4 times 2 is going to be 8. 8 plus 1 is going to be 9. So we'll have 9 inside that parentheses. And the whole thing is over h. That's a popular thing for a lot of people to forget. All right, that's looking pretty good, but we need a little bit more. So let's simplify. I'm going to take this power of 2 right here, and I'm going to be distributing it to all of my terms that I have inside the parentheses. When I'm doing this, I like to have my h squared term first, so I'm going to bump it to the front, and I like to have my constant term in the back, so I'm going to do that as well. So let's take a look at what that's going to be. So I'll have my limit still. Got to make sure you write down limit, kind of an important thing. So make sure you're doing that. 2 times h squared is going to be 2h squared. Then I'm going to do 2 times 4h, which is going to be 8h. And then I'm going to do my 2 times 4 with my 8 at the back here. Still have my plus 1 right there. Don't forget about your plus 1. And then we have a minus 9 at the very, very, very far back right there. And an h on the denominator. Great, I can still continue to simplify. Specifically, the thing that I'm most excited about is this chunk right here. If you look closely, 8 plus 1 is going to be 9, minus 9 is it's going to go away. That whole thing is just going to be gone, and we're not going to have to deal with it anymore. So that's going to leave us with just these 3 terms over here, which is going to be pretty great. So let's take a look at what that's going to be. So we'll still have our limit, as still as h approaches 0, and we're going to have 2h squared plus 8h over h. Now something you might notice here is that we have h, and h, and that is really important because that means that probably something can cancel out. The formal way to do this is to actually factor out the h first, which would be like this, and you have your 2h plus 8. Some people say, hey, Mr. Slomka, can I factor out more if I wanted to? Yeah, sure. There's a common factor of 2 there, and you can pull it out. But you won't be able to cancel that out. It's going to stay. So it's up to you if you'd like to factor out the h or 2h, whatever you pick. I just leave the 2h where it is and the 8 where it is, and I just pull out the thing that I know will cancel. Cool. That thing right there, that is something that I can direct substitute for, and it'll work out really nicely. I would not have been able to direct substitute to begin with, but I can definitely direct substitute now. If you plug in a 0, 2 times 0 plus 8, 2 times 0 is nothing, and your final answer is just 8, which is pretty cool. I will show you how to get that answer of 8 extremely quickly from an equation like this, but not until after the Chapter 12 test. So this is the way that we're going to be doing these kinds of problems right here. But we will learn faster techniques, and you will definitely learn better techniques when you go to calculus class. Let's take a look at the second page. So now for our second page, what we're going to do is we're going to talk about breaking down a limit a little bit more. So up here at the top, what we have is what is called a one-sided limit. And a one-sided limit is where you're going to take a limit from just the left side or just the right side. A lot of times when we're working on our limits, we move from the outsides in. So from the left and the right simultaneously. But with these limits, what we're going to do is we're going to do just the left side or just the right side. The notation for this is pretty basic, but it also can be a little confusing, especially this one right here. So what you have right here is you've got your normal limit of f of x, and it says as x approaches c, but then after the c, kind of where the exponent would be, there will just be a little negative sign or a little positive sign. That negative sign means approach from the left, like where the negative numbers are on the x-axis, and the positive sign means approach just from the right, where the positive numbers are on the x-axis. For some reason, I don't know why, but there's a lot of kids who see this and they think, oh, it must be a typo. He must have he was supposed to write the negative in front. It's actually negative c. No, that's not true. Or they see this one, they say, oh, it's a typo, and he's just writing that plus sign for fun. And that is also not true. So you have to make sure that you understand what those things signify. And that means from the left or from the right. Let's take a look at a popular example. So we have seen a limit that looks very similar to this with the absolute values before, and we've had a graph like this, and that was actually from the first day. And one of the things we had said is the limit of a graph like this does not exist. Limit does not exist. There's a little shorthand for you. Because what you have is you have these two things, and as you approach the center, they are not curving towards each other. They're not getting any closer. They're not getting any further. They are doing what they are doing. And if I had to guess what they would continue to do, I'd say they just shoot right past each other like two ships passing in the night. But that's not what we want. We want them to kind of come to the same point, and they're not doing that. Here's the weird thing, though. If you break the problem down and you look at it as the limit as x approaches 0 from the left, which is what this little negative sign right here means, then it becomes a very different story. If we're taking a look at this graph and we're only interested in what's happening as we move from the left, you will get a very different story. Right here, we've got this line that is just kind of cruising along, and specifically it's cruising along at, surprise, surprise, here's -1, so that's going to be actually -1/4 right there. So this is -1/4, -1/4, -1/4. As we move from the left, as we're moving closer and closer to an x value of 0, -1/4, -1/4, -1/4, -1/4. It's not really changing. It's always -1/4. So that means that the limit from the left is actually -1/4. There is an answer this time. So over here, when it was regular, it just says the limit does not exist, but over here we have an answer. Similarly, when we've got the limit as x approaches 0 from the right, because we've got a plus sign here, you actually can get another answer. This time from the right, if we were moving just from the right over, not the left anymore, then what's going to happen is we're at +1/4, +1/4, +1/4, +1/4. It's not getting any bigger or smaller, it's staying the same, and so that means that that limit would also be +1/4. There is an answer right here. So now you might say, well, what's the connection between these things and this thing right here? It's the same connection that we've talked about. Because these two answers are not the same answer, that is why the limit of just x approaches 0 is unexistent. It does not exist right there. So these two things, they are good answers, but when you put them together, they create a bad answer, or a limit does not exist situation right there. So that's kind of exciting. Here's another piecewise one that's kind of like that as well. This one says find the limit of f of x as x approaches 2. So here's what we're looking for. We're looking for the limit of f of x as x approaches 2. That's what we're really after. So we have a piecewise function, and if you look, you cannot direct substitute for this one. There is no or equals to 2 here. It's just less than 2 or just greater than 2. Because there is no or equals to, and we cannot direct substitute, we're going to have to do something different. So here's what we're going to do instead. We are going to take two limits and put them together. So my first one is going to be the limit of f of x as x approaches 2 from the left. So I'm going to add on a little negative sign. And the second one I'm going to do is I'm going to do the limit of f of x as x approaches 2 from the right. So I'm going to add on a little plus sign. I'm hoping to get the exact same answer for both of these. If I can get the same answer for both, that will be the final answer. If I get two different answers, then it's going to be a lot like this case up here, and that will be my final answer. So let's try it out. When I say x approaches 2 from the left, what I mean is smaller numbers than 2 and getting bigger and bigger towards 2. So what I'm talking about is I'm talking about this top case right here. So that guy is going to go to work. I am going to be interested in 2. So what I get to do is I get to cheat, and I do get to direct substitute, but into the top one because it's from the left, left meaning less than. So that's going to be 2 squared plus 1, or 5. For the bottom one, since I'm doing 2 from the right, that means I'm taking bigger numbers that are larger than 2, and then they're getting smaller towards the 2. And that is actually the deal with this bottom one right here. That says x is greater than 2, so that's what we're going to do right here. Once again, I get to cheat, and I'm going to be able to direct substitute into this one right here, and hopefully I get a very similar answer. Let's find out. -1/2 times 2, and then plus 6. Well, that's going to turn into a -1, plus 6 is going to give me 5. There you go. I got the exact same number 2 times. I could not have direct substituted with just a regular 2, but because I did it twice with the from the left and from the right, I can now say that my final answer for the entire problem is 5. Last one right down here. This is a good story problem, and it really kind of gets to the concept because there's not a lot of math here. So if you can master this concept or maybe guess what the answer is going to be before I say it, that would be really, really cool. It says Tabitha wants to ship a package that weighs X pounds. FedEx charges more money when the packages get heavier. The function c of x shows how much FedEx charges. Use the given information to find the limit of c of x as x approaches 3. So basically what was happening here is that Tabitha wants to ship a package that's about 3 pounds. And so she's approaching 3 pounds. So here's what we're after. The limit of c of x as x approaches 3. But in order to do that, there isn't going to be a great direct substitution thing, because what's happening here is that it's about 3. We don't know. You know, when you're filling up a box, it's not going to be like dead on 3 pounds. It might be a little bit more, or it might be a little bit less. So this is kind of a story problem where there's some wiggle room, because we live in a world where, you know, gas costs $2.98 and 9/10 of a cent, and nothing's very nice and perfect and square the way it ought to be. So once again, I'm going to do the problem very similar to what we have right here. What if Tabitha's box is approaching 3 pounds and it's kind of approaching it from below? Or what if Tabitha's box is a little bit over 3 pounds and then maybe she starts taking some things out, so it's approaching from above? Let's take a look at what we're going to have here. So if we do it this way, the way that seems to make sense for the problem, what's going to happen here is from below, that means that we would start off with values that are smaller and work our way up, which is right here. It costs $11 for any box that is 2 pounds all the way up to 3 pounds, even including 3 pounds. So that would be an 11 right there. This one, if Tabitha's box is over 3 pounds and then she starts taking things out of the box, then that would be for this guy right here, from 3 pounds all the way up to 4 pounds, but not really including 3 pounds. But here's the thing though, if it's just a little bit over 3 pounds, it's going to be $12. So now here's the strange thing. For our final limit, the answers are inconsistent over here, so that means for our final limit, as x approaches 3 without any plus or minuses back here, the limit does not exist. It is not going to work. That really rubs a lot of people the wrong way. They hate that. They say, hey, it should be this number because it's or equal to 3. Well, it doesn't matter. It is all about what it's approaching. And in this situation, it is specifically approaching from both directions. So this one right here is one direction, and it makes a lot of sense to most people, but you also must consider this guy right here, because there is a situation that you can easily explain. Her box was too heavy. She started taking things out. And so that one also needs to be taken into account. So the limit does not exist. But with that also in mind, I mean, it does make a lot of sense. Most people, they don't take things out of a box. What you do is you fill up the box, or at least you fill up the box first. So it says, what if we only approached it from the left? So for from the left right here, which is the more logical way as far as most people are concerned, myself included, then the answer would just be $11. So that makes a lot of sense. I get that, and I agree with it. But as far as mathematics and limits are concerned, for this top one, the limit does not exist unless stated specifically that Tabitha's box started off light and then it got heavier and it never got lighter again. So that's all the limit from both sides stuff. It's a cool concept, and it'll help you break down your limits a little bit more so you can understand them piece by piece. But you have to watch out for inconsistencies like this, because it feels so right to say this, but you have to also take this into account. On the very back page, what I have is I've got some you try it problems for you. So I've got some answers that I'd like you to take a look at right here, so you can kind of see what I did, how I got my final answer. There's your first one right there, and then here's your second one right there. If you have any questions, come talk to me. If you need the homework assignment, you can get it from me or from one of your classmates. I'll have more videos for the other lessons as the week goes on. Thank you.